So now that we understand a little bit more about how the electrons are flowing through the pipe, there's something on the other end of the pipe that is receiving them, right? And there's software inside those devices that allow us to measure those electrons and then give us some visual displays of what that actually looks like in both the time and frequency and amplitude domain in some cases. So I think that's a good place to jump into the RF spectrum display section. Let's start with the basics, Larry. When we look at the downstream spectrum using something called full band captures on full band capable devices, what are we looking at here?
Yeah, okay, so first of all, a little history on the full band capture. People might think this actually costs something, like it slows the modem down or it takes additional processing. And the reality is all modern receivers use this digital analog to digital conversion technique, and we're capturing all of that spectrum in the time domain and then converting it to the frequency domain and using it to do that slicing that we talked about into symbols. So as part of that process, we just added a little buffer to the cable modem and say, well, let's keep track of all of those so we can take them out and use them for analysis later. So we can use it to kind of reverse engineer what's going on and figure out what the problems are. So that's what we're going to talk about now. These visualizations, Mike, I'll talk about a couple, and then maybe you can take everybody through the vacant spectrum and how that looks. On the top left, we have our 6 megahertz SC QAMs. This is what we've been doing for a long time in the downstream. And then our newer OFDM channel. In this case, this is 96 megahertz wide. And then you'll, so that you won't see those guard bands in the middle of an OFDM channel. And then you will, but you might also see a notch that was intentionally put there. And in the center image is the pilot tone. It's just a CW. And these are used for a number of things. It might actually be an analog television station if you're still carrying analog. Comcast, we generally aren't. Some systems we are, but generally not. Then we have guard bands. Those are the little notches in between the SC QAM channels. That's used to prevent interference and allow for the shoulder area and the roll off of those SC QAM. And that is actually known as a raised root cosine filter that creates that QAM shape. And then finally, in between the QAM and the OFDM, we have typically a little bit larger guard band, and that's just to help reduce potential interference across the power that's associated to those channels. Mike, why don't you take everybody through the vacant spectrum?
Yeah, I want to pop back to that CW carrier for a little bit, just for a second. So that CW carrier is obviously very, very narrow, right? And they're in there sometimes for different reasons. They could be for doing leakage in the lower aeronautical down around 108 to 138 megahertz, or in some cases to support older legacy amplifiers, we'll have an analog ALC, which is likely what this one is, right around 499 megahertz. That's a pretty typical analog SC channel. However, we can't measure CW carriers the same in these tools as we can the combined power of the QAM channel. We'll talk more about that later, about how we can translate the power as it's represented on these display tools versus what the actual power would be measured in the system. So more on that later. In the bottom few images, we have different views of vacant spectrum. So in this instance, centered right around 400 megahertz, we see this gap in our visualization of tools. But if you look closely at the bottom, you'll see some things that look like low-level CW carriers in between our SC QAMs. Now, we'll talk more about those too. Those are artifacts. Those aren't actual signal channels, but they're artifacts of the construction of this data into a visual image. In other cases, you may see larger chunks of vacant spectrum as the channel plans in your system are moved around. You can add DOCSIS channels to get more downstream throughput, or rearrange your linear video channels to make room for more DOCSIS channels, or OFDM for future expansion, etc. So you may see big portions of vagrant spectrum, which in some cases is very useful because it allows us to see the noise floor of the receiving device in between the channels. So vacant spectrum can be very, very narrow, like 1 6 megahertz channel spacing that's left vacant intentionally, or it could be a missing channel because of a hardware malfunction in the head end or something else. But vacant spectrum can look different depending on the received device, and I think we'll talk more about that in a bit. Okay, moving on, other things you should know.
This is really important because there's a bunch going on here that you won't see in a normal spectrum analyzer, like a really lab grade piece of equipment. Don't forget, we're talking about a cable modem that's been trained to act like a spectrum analyzer. So there's a couple of things going on here. I'll take the top one, Mike, that you need to know about so that you don't misinterpret what you're seeing versus maybe a regular spectrum analyzer you'd be using in a lab. First on the top is that we have this diplexer. Don't forget, cable modems, at least in today's architecture, they have different lanes for upstream and different lanes for downstream, and they separate those lanes with a diplex filter. And so what happens is we're actually reading from the downstream perspective of the cable modem. That means you can't actually see what's going upstream because there's a filter blocking that from the view of the cable modem. That's what we see here in this diplex rejection area. You will notice, and this is really important, you see this big, large hump of energy there? That's not supposed to be there. That's noise. And now, if that diplex wasn't there blocking that noise, you would actually see that in the upstream, which is the area that's being blocked there. So just know that most of these have different types of diplex filter implementations with different locations, different rejection properties. So how you interpret that spectrum there, you should be very careful about because of that reason. But do pay attention to that additional noise and stuff that's not supposed to be there. That should be very clean with just downstream SC quams there. So that's that. And I will say on a little bit, and I'll let Mike take over, this the spectrum where you see this really raised energy there in what would normally be the return band, that's actually a feature that we're working on that allows you to measure the upstream spectrum from the downstream perspective, which is incredibly powerful when it works properly. That's called the upstream diagnostic analyzer. When you see that raised, it looks like an OFDMA transmission, but don't confuse it. It's not. It's a constant. That's actually the noise power in the upstream. And so you will occasionally see bursts there from the upstream transmitters around other customers and maybe modems within the home. But that's what we call the UDA spectrum. For now, ignore that, but there's a lot of neat stuff coming there. What else, Mike?
Yeah, so that is important, right? Especially in systems where maybe you've done a mid-split deployment and enabled OFDMA in your upstream. And it's easy to misrepresent this as a consumer of tools and say, oh, well, we just turned on OFDMA in that spectrum. That must be what it is.
Yeah.
What's really important is to understand the model and the make of the device that you're looking at, right? So for the top spectrum capture, that is potentially something like a video set-top box that has a DOCSIS chipset in it. And those would have fixed subsplit diplexes here around 42 megahertz, right? So your diplexer rejection is 42 megahertz to 5 megahertz. However, other devices, newer DOCSIS 3.1 devices, may have switchable diplexes so that they can be configured to work in mid-split operation, in which case the diplex rejection moves out to about 85 megahertz. So this would be a mid-split capable device that has diplex rejection to a higher frequency. So understanding which device you're looking at And then to Larry's point, not all mid-split capable devices will have this UDA spectrum in them. It's very manufacturer specific based on the chipsets that are in the device. So you may look at one DOCSIS 3.1 wireless gateway and see this, and look at another one and not see anything at all. But the diplexer rejection, if they're set into mid-split mode, could be out to 85 megahertz for both of them. The other information that's in here that's super useful is this FM ingress between 87.9 and 107.9 megahertz on both of these devices. So they're above the diplex rejection, but they indicate that there's some noise in that FM portion of the spectrum. So just a few things that you should know as you're beginning to analyze these downstream full band capture spectrums to help you properly interpret them. Some other things you should know are, I'll let you cover this one, Larry.
Sure. These artificial noise spurs, you'll see they're at exactly 7.5 megahertz for a reason. That is not noise. That's not real. If you hook up a lab grade spectrum analyzer, you won't see that. That's just an artifact of a stitching mechanism that they use in the Fourier transformation. In Fourier, they happen to take these 7.5 megahertz chunks and stitch them together, and they align them by inserting an artificial tone in software to make them line up, glue them together, and transform them. So don't worry about it. It's incredibly nerdy, not important to you. Just know that that's not a real thing. That's an artifact of basically the process to bring it to your display, like Mike said earlier.
So we mentioned when you see them in the vacant spectrum between active channels, they can look like CW tones, but they're not real. The other one would be this switchable diplex notch artifact, right? So we mentioned that certain devices can be mid-split, high-split, sub-split capable, and there's a function of the switch inside the device to change the diplexer frequency. And sometimes that can result in an artifact at one of those diplex filter frequencies, in this case, 85 megahertz. So pay particular attention to, one, the device, like we mentioned. Is it a sub-split only device, or is it a switchable where it could be potentially sub-split, mid-split, or potentially high split? So other information you should know. And finally, the power relationship. We alluded to this previously. So as Larry mentioned, we take all of these tiny slivers of signal and reconstruct them into this downstream display. And I think we'll talk more about RF spectrum display and resolution and video filtering also, Larry. But depending on the device and your software and what bandwidth of energy you're measuring, the resolution bandwidth measurement is important, there is a correction factor. So in this instance, I think we're using, what, 117 kilohertz resolution bandwidth or something in that neighborhood?
117.1875 to be precise. And if you measure the amount of energy in that thin of a channel, that's actually about 17, it's 17.1 dB lower than the 6 megahertz cumulative. So if you add all those up in those 117.1875 kilohertz slices and accumulate 6 megahertz worth of that power, that adds about 17 dB to the total power, and it's 17 dB off. So that's why we put a little visual reference in there for you to. So
in this example, if we're looking at the downstream receive powers right around 0, right? But that's equal to, in the visual reference, the peak of those carriers at about -17. So when you're looking at your full band capture display, pay attention to your vertical axis because 0 is approximately -17 dB in this scenario. Okay. So this is how we're conditioned as technicians from day one, right? In the vertical axis, we think of amplitude or level, not always in power, but in level, in dBmV. And then we're also conditioned to look at a spectrum or any kind of plot with frequency in the horizontal axis with our return path being all the way on the left, from 5 megahertz to 42 or 85 or 200 if you're doing high split. And then your downstream is everything that follows after that, right, in the frequency domain. So this is how we're conditioned to think. When we're measuring levels, we measure what frequency it is and what our amplitude or power is. So when we visualize that on spectrum analyzers or any reference display that shows signals, it's typically in the amplitude is the vertical axis and frequency on the horizontal axis. Do you want to cover this one, Larry?
Sure, yeah, you bet. The one difference between the cable modem spectrum analyzers and an actual spectrum analyzer is that one of the limitations of a cable modem is they're slower, a lot slower. And that's because it's not actually, its ability to capture spectrum is pretty limited in terms of width. Then it has to add them up together after a number of samples, save them, and then display them or present the data so we can display it externally. So the problem with that is in order to achieve a really nice crisp visual line of a power spectrum, you typically average that a little bit, and then the line power gets a little bit more less noisy visually. And so that takes time. You have to collect everything, store it, collect it, store it, and then average all of these samples out. So you can tell what you're seeing here, like that nice tight line on the top happens to be a cable modem with a chipset and firmware that does really good averaging for us so that we don't have to collect it and do it externally. And the one on the bottom is one that doesn't. It's just a little bit slower, and we don't have all day to wait for these things. So you'll see that those are two different devices telling you exactly the same thing. One just happens to be better at averaging it so that it has a nice, easy to read line, and the other has a subject of less averaging. Averaging also hurts you in some ways. If you're looking for really high spurious noise, for example, you can have one spur that gets beat down in averaging so that there's different functions: peak hold, min hold, average, live traces. These are just kind of functions that you use for different reasons in a spectrum analyzer.
So we've referred to resolution bandwidth before, and how it influences how the traces are represented on your visualization tools. So at the top, I love this graph because this is really a good illustration of how resolution bandwidth can affect what you see on a spectrum analyzer. So instead of starting left to right, I actually kind of want to start right to left and say we have these three tones, right? A center tone and two adjacent lower level tones. And with really good or high resolution bandwidth, meaning 1 kilohertz slices of spectrum that are being analyzed at a time, and that's really what that means, is how wide is the lens that we're viewing the spectrum through. With really high resolution, like 100 hertz, you can see that we have three tones that are very narrow and very precise. But if we widen the lens and we look at the same spectrum, you can see the same three carriers are still there, but they're a little less distinct, and the resolution at the noise floor level gets a little worse. And then finally, if we look at it through a really wide lens, as we sweep through there, we're just going to see one hump of energy. So we lose the granularity of seeing the reality, which is that there are three very precise, very narrow tones. So resolution bandwidth does affect how the signals are visually represented on the device that you're viewing. So on a really good lab grade spectrum analyzer, you can change the resolution bandwidth settings to get really precise measurements and a really good look at the noise floor. But in other devices that don't have that same level of precision in the resolution bandwidth, the signals, while they may be the same, can actually look different. And that's important to understand when you're viewing anything in the spectrum, amplitude and frequency domain, is to what you're visualization or your display is set to. So you want to walk us through the examples at the bottom, Larry? And
Oh yeah, we can make this one quick. So these are really exactly the same spectrum, but the perspective of two different cable modem makes and models. The one on the right is a very old, the very first version of full band capture on a 3-generation old chipset. I won't say which, but it just has low resolution bandwidth. And the reason for that is because it actually doesn't have enough spare CPU to actually process and memory to store the high resolution data. It's just a very limited set of extra memory and processing power in these old cable modems, but we were still able to train them to do the spectrum analysis. So I view it like, a coarse view of the spectrum is better than no view, which is totally true. But you can see the difference between, the power levels and the resolution, because the one on the left, exactly the same spectrum, but a more contemporary version of the chip that has higher resolution, more speed, more memory, so that it can do averaging and all this other stuff. So just examples of what those look like when you're looking at the tools and interpreting it. Resolution bandwidth is important concept to understand.